Okay, so this video is solving quadratic inequalities in one variable, but our first worksheet is graphs of linear inequalities in one variable. And I'm basically going to run through some of these, but not necessarily all of them with you, and you can check your answers with the answer worksheets. Okay, x is less than or equal to negative 4. Any value of x that is less than or equal to negative 4. In order to indicate equality, we use a solid dot, and then all values of x that are less than or equal to, and I'm just going to come up above the number line here. So I'm not drawing on top of it to show x is less than or equal to negative 4. In the textbook, when they do this, they'll use a colored line on top, and I could do that as well, but you can't, so let's just draw above. X is greater than or equal to negative 4. Solid dot again indicates equal to negative 4, and then we want to be greater than, so we go to the right. X is strictly less than negative 4. Open dot. So we use an open dot to indicate that negative 4 is not part of the solution, but any value less than negative 4 is. And this one will be an open dot again on negative 4 and greater than, so we're moving to the right, larger than, numbers that are larger. And just if you want to check any number, just take a value. So negative 5 should make this true. There's negative 5. It is less than negative 4. Negative 5 makes this false. It's not part of the solution set, but 0 is larger, so 0 is part of the solution set. Okay, let's do these guys. Negative 4 is less than or equal to x, which is less than or equal to 2. So negative 4 is less than or equal to x, which is less than or equal to 2, which is just the way of saying that x lies between negative 4 and positive 2. Here, same thing, but it's strictly less than, so x negative 4 is strictly less than x, but a negative 4 is not included as part of the solution, nor is 2. Negative 4 is less than or equal to, but 2 is not included as part of the solution. And in this case, negative 4 is not part of the solution, but positive 2 is. Okay. And now we want to interpret. Let's move on down. Write the inequality that represents each number line. In this case, x is between 1, 2, 3, 4, 5, 6, 7. X is between 1 and 7. So we start with the lower bound, 1, less than or equal to solid dot x, which is in turn less than or equal to 7. Here we have open dots, negative 3, negative 4. So negative 4 is strictly less than x, which is strictly less than 0. 3, 4, 5, 6. Our low end is negative 6, less than or equal due to the solid dot x, which is strictly less than, where are we, 3, 4, negative 4. And lastly, negative 2, less than x, less than or equal to 3, 4, positive 4. So that's our notation for inequalities and number lines. Right, inequalities in one variable. Okay, so how do we solve quadratic inequalities in one variable, which is really the point of what we're doing? A quadratic equation is one that can be expressed in the form ax squared plus bx plus c equals 0, right? We've been studying quadratic equations to this point. A, b, and c are constants, and a can't be 0. If a were 0, then that would take out the quadratic term, the squared term. A quadratic inequality in one variable can be expressed as one of the following four forms. Strictly less than 0, strictly greater than 0, less than or equal to 0, greater than or equal to 0. And we can solve a quadratic inequality in one variable by one of the following methods. Graphing the corresponding function, using roots and test points, using sign analysis, and using case analysis. So let's start this out using a graph, graphing the corresponding function. So here, the partial graph of y equals x squared minus 2x minus 8 is shown. Use the graph to solve. When is x squared minus 2x minus 8 equal to 0? Well, this point here and this point here. So this would be x equals negative 2 and x equals positive 4. We can express that as a solution set. Brace brackets, negative 2, 4. Okay, don't put it in parentheses. That would make it an ordered pair. When is x squared minus 2x minus 8 greater than or equal to 0? Well, here's where it's greater than 0. And, we'd say partial graph because we don't have arrows on there. And also, here's where it's greater than 0. So in this case, we could say that x is less than or equal to negative 2. Okay, the equal here because of the equal here, right? It's equal to 0 at negative 2. And also, if x is greater than or equal to positive 4. Okay, and in that case, the x squared minus 2x minus 8, the graph, right, is that all the values are greater than or equal to 0. If I put a value of 5 in for x, I will get a value greater than 0 for this expression, and that will make that true. Okay, I'm going to do one more for you. When is x squared minus 2x? Oh, let's skip that one. I think you can do that. What you have to keep in mind, the only difference here is that this is strictly greater than 0, so it won't be including. And what I will do is part E, leaving C and D for you. X squared minus 2x minus 8 is less than 0. So what we're looking for in the graph is our key values, which is where it's equal to 0. And we can see that it will be less than 0 as long as it's between these two key values. And we just spent the time writing linear inequalities. Negative 2 is strictly less than x. Okay, we can't be equal to, we're not equal to 0. That would be the answer for D. Negative 2 is strictly less than x, which is strictly less than 4. And this is how we express a range of values from negative 2 to positive 4. Solve each of the following inequalities by graphing. Round your answer to the nearest tenth where necessary. Basically, what you want to do is graph these, find the intercepts, and then use those values. So, whoops. Let's take one of these. We'll do one, and I would do this in class as well. If I were doing this with you, I would do one of these. So negative 2x squared plus 4x plus 7. Okay, so on my graphing calculator, I want to graph y equals, I can't really graph greater than 0 on this, but I can graph negative 2x squared plus 4x plus 7. We'll hit graph. We're interested in the intercepts. Now, my way of doing intercepts is to do an intersect with 0, so I'm going to just regraph. Go second, calc. Number 5 is intersect. I'm going to move down to about the point of intersection, hit enter 3 times, 1, 2, 3. Negative 1.1. So let's sketch this out here. Negative 1.1. Rounded to the nearest tenth. Let's bring the calculator back. Second, calc. Number 5 is intersect. Now, it'll be easier to move along the y equals 0 line than to go all the way up and back down. So I'm just going to move to see how I've moved to y2 equals 0. And when I trace, when it's asking for the first curve, I don't care if the first curve is y2 or y1. I'm going to hit enter. First curve. Second curve is now the parabola. And here's my guess. And that's 3.1. So let's go over here. X is equal to 3.1. Now, we want strictly greater than 0. Here are the values that are greater than 0, right? This is above, because this is what our graph looks like. We don't want to include these x values because we're strictly greater than. Okay, if we were less than or equal to, greater than or equal to, we would include those. A formal writing of this would be the set of all x such that negative 1.1 is less than x, which is less than 3.1. And that would be a formal rendering. So negative 1.1 strictly less than x, which is strictly less than 3.1. You can, of course, graph these out yourself. What we're really interested in, what are we interested in, right? We're interested in the intercepts. That's our point where the function is equal to 0. If we want it to be greater than 0, then we need to be up above the axis. And if it's greater than, if we want it to be less than 0, then we want the points that will be below the axis. Although this 3 of these guys open. Well, these two are the same function, so once you've graphed it, you're doing the part, seeing as it opens down, you'll be doing the part that's above, just like here. And for this one, it will be basically everything else. And again, this opens like this. I don't have the axis in here, I guess. Well, let's go back, look at the graph again. The axis is somewhere here. Okay, that's the y-axis. But really that doesn't matter, right? What matters is finding the x-intercepts. Write a quadratic inequality in simplified form that has the given solution. Well, let's take this and we will graph this. So A or B. Okay, I'll do A. Now you notice it's going to say a quadratic inequality. There could be many of them. Negative 3, so let's call that negative 3. Call this 5. Now I could draw a quadratic inequality like this, opening up, or I could draw one opening, well, let's just do one opening up. Now, since these are the x-intercepts, remember a little thing, right? These are 8 units apart, so 4 units. Where is my axis of symmetry, right? It would be x equals 1. I don't know where the vertex of this is, and really it would depend on what stretch factor I chose to give it. But let's say this is our somewhat shaky quadratic. So my solution is that I want x to be between negative 3 and 5. In this particular case, these values will be below the axis because I've chose to open this up. Maybe we'll do another one where we open it down. This is the intercept, the corresponding root. So if I know that x equals negative 3, then x plus 3 equals 0 is the corresponding factor. If this is x equals 5, then x minus 5 is the corresponding factor. So in factored form, I'm graphing y equals x plus 3 times x minus 5, which is x squared minus 2x. X squared minus 5x plus 3x is minus 2x minus 15. And here what we have graphed, since we want our solution to be this part here, okay, this is the quadratic function. The quadratic inequality would be x squared minus 2x minus 15 is less than or equal to 0, right? Less than or equal to because we are including the zeros. X squared minus 2x minus 15 is greater than 0 would be the branch here going to the right and this branch here. Had I chosen to draw the equation like this, then it would have opened down. There would have been like a negative here. I could have really I could have put a negative 2 or something. Made this negative 2x squared plus 4x plus 30. That would be another quadratic, would be this quadratic quadratic function. And then if I wanted the values to be the solution rather, if I wanted the solution to be here, then I would have negative 2x squared plus 4x plus 30 is greater than or equal to 0. Okay, again, what might that look like? Let's just redraw this to keep it clean. Negative 3 and 5 are my intercepts. I'm making this open down. My axis of symmetry is still x equals 1. Here's my vertex up here. So I chose to say this would be the equation, and I'm giving it an a value. I'm just going to say negative 2 because it's any quadratic inequality in simplified form. X plus 3, right? The important points are where the x-intercepts are, and x minus 5 simplified this quadratic inequality is negative 2x squared plus 4x plus 30. And the inequality then becomes, since we want these values here, we are looking for where this quadratic function is greater than or equal to 0, and that will give us a solution where we are between negative 3 and 5, and we're including both. Okay, roots and test points, another method of solving. First we solve the corresponding equation. And the equation will be where it's equal to 0, equals 0. So let's solve by factoring. We have many methods of solving equations. We are going to hope that this one, let's see, that's plus, they're both the same sign. I'm going to go with a minus 5 there and a minus 1 there. Okay, let's check that out. 2x squared minus 10x minus 1x will be minus 11x plus 5. So that's the corresponding equation. What are the roots? So x will be 1/2. And for this one, x will be 5. Plot the roots on a number line. Okay, let's say that's 0. There's 1/2. And here's 5. So these are the points of interest. And what we need to do is we have a number of intervals. So this number line is split into an interval where x is less than 1/2, where x is between 1/2, so 1/2 is less than x is less than 5, and where x is greater than 5, right? And then we have our 2 points where x is equal to 1/2 and where x is equal to 5. And what we want to do is we want to see what's going on in each interval. So we're going to take a test point in each interval. Okay, so x is less than 1/2. Well, 0 makes a very good test point. So I'm going to choose 0 as the test point. I'm going to substitute that into this into the equation, and I'm going to see if it makes 2x squared minus 11x plus 5 greater than 0. Okay, so we're going to go 2 times 0 squared minus 11 times 0 plus 5, which gives us 5. Is 5 greater than 0? Yes, it is. So then things are true if x is less than 1/2. How about between 1/2 and 5? So we pick a point. Really, any number between 1/2 and 5 will do. So my test point is going to be, I'm going to go with 1. So 2 times 1 squared minus 11 times 1 plus 5. So this is 2. Minus 11 is negative 9, plus 5 will be negative 4. Is negative 4 greater than 0? No, it is not. And we need an x value greater than 5, any number greater than 5. Well, let's pick something that squares easily. So let's say 6. So 2 times 6 squared minus 11 times 6 plus 5. So 6 squared is 36, times 2 is 72. 72 minus 66 is 6, plus 5 is 11. Is 11, that's the value you got, greater than 0? Yes, it is. So we say yes. So that means that values that are less than 1/2 work. Values between 1/2 and 5 do not. And values that are greater than 5 also work. So these are this is a drawing of what works, and now we can state this. So x is less than 1/2, x is greater than 5. Okay, so one more time. What are we doing with roots and test points? We're solving the quadratic equation. Okay, however you want to solve. Factoring, I always try factoring first. Completing the square, quadratic formula. You have to find these roots. We plot the roots on a number line. We then have to examine each of the intervals where x is less than the leftmost root, in between the two roots, and greater than the root. Would this, should this, could this, had this been an inequality of greater than or equal to, then we would have used solid dots here and we would have included the 1/2, right? Then in our solution would be a less than or equal to, or a greater than or equal to, not strictly less than or greater than. All right, what else? Sign analysis. Sign analysis. Okay, one step at a time. Solve the corresponding equation. Okay, we've got negative x squared plus x plus 6. Oops, sorry, we're going to solve the equation, so we're going to write equals 0. I don't like negatives, so I'm going to get rid of that. So I'm going to go x squared minus x minus 6 equals 0. X minus 3, x plus 2 equals 0. Okay, I kind of factored by just sort of looking at it. Let's check it out. X squared plus 2x minus 3x is minus 1x minus 6. Okay, so our solutions, x equals 3, x equals negative 2. Plot the roots on a number line. There's negative 2, and here is positive 3. We're now going to express the original inequality. This is the original inequality. Remember, I changed things around. When you're equals to, you can do stuff like multiply both sides by a negative. We need to express the original inequality in factored form, and each interval we're going to state the sign of each factor. Okay, the original inequality is that negative, so it'll be negative 1 x minus 3 x plus 2 is less than 0. We're going to combine these. Since the negative 1 is just a constant factor, then we're going to combine it with the negative, with the x minus 3 to make it, we'll consider this a single factor, and we will consider this to be a single factor. So, what have we got? All right, let's write down, we've got the negative 2 and the 3. That's our points. We've got the factors, negative 1, x minus 3, and we've got the factor x plus 2. And we have the 2 together, negative 1, x minus 3, x plus 2. So what we want to do is we want to look at negative 1 times x minus 3, and we want to look at that when the values are below negative 2. So we can just take an example. If values below negative 2, let's say negative 3. Negative 3 minus 3 would be negative 6, times negative 1 will be a positive value. So anywhere in this interval, x is -5. This will be a negative. When you multiply that by a negative, the result will be positive. Taking this factor in this range, let's use 0. So 0 gives me -3. Here, times -1 is also a positive. So anywhere in this interval, for example, how about 1? You put a 1. 1 minus 3 is -2 times -1. All the values of this particular expression will be positive. When x is greater than 3, how about 4? 4 minus 3 is 1 times -1 is negative. So in this interval, all values of this factor will be negative. Okay, x plus 2. All right, let's take an x value that's below -2, -10. -10 plus 2 will be -8. It'll be negative. How about -3? -3 plus 2 is -1. This will be negative. Here, 0. 0 plus 2 is 2. In this interval, the values of x plus 2 will always be positive. Okay, put a 1 in there, you get a 3. Greater than 3, well, we're just adding 2, so really it will be positive. When you combine the factors, okay, if we combine a positive factor with a negative factor, we end up with a negative for the expression. Combine two positive factors, you get a positive. Combine a negative with a positive factor, you get a negative. Had there been two negatives, which wasn't in this case, a negative times a negative would have given us a positive. So what we're looking at from this number line is we want this expression to be less than 0, which is negative, and that expression will in fact be less than 0 or negative. Can't find, oh, here we go. It will be negative here and here. So what intervals do those correspond to? X is less than -2 and x is greater than 3. And again, because this is a strictly less than, then we won't have any equal to. So state the solution. X is less than -2. X is greater than 3. Case analysis. Solve 3x squared is strictly less than 7x minus 2 using case analysis. Make one side of the inequality 0 and factor the inequality. Okay, let's make the right side. So 3x squared minus 7x plus 2 is less than 0. Factor, well, we're going to have a 3x and an x. They're both the same sign. They're both negative. To get a 7, I'll put a 2 here and a 1 here. Say that's less than 0. Let's double check that. 3x squared minus 6x minus 1x is minus 7x plus 2. So we want to now write the two cases for the inequality to be less than 0 or greater than 0. In this case, less than 0. And we're going to solve that pair of inequality. Okay, since this product has to be less than 0, it has to be negative, that means that either 3x minus 1 is less than 0 and x minus 2 is greater than 0. So we need one negative and one positive. And the two cases will be this is the negative and this is the positive, and then vice versa. Okay, so let's solve these inequalities. So 3x is less than 1 and x is less than 1/3. And over here, x minus 2 is greater than 0, x is greater than 2. So what we want to do is we say, well, x is less than 1/3 and, right? And it has to be at the same time. X has to be less than 1/3 and at the same time greater than 2. That might not work out so well. Let's take a look. Let's say here's 0, here's 1/3, and here's 2. And we've got the same number line here, 1/3 and 2. So x is less than 1/3, that's anything from here over, and at the same time x has to be greater than 2. Well, we can see that that can't happen. There are no values that are down here and at the same time up here. Okay, so there are no solutions to make both inequalities true for case 1. Okay, so no solutions for case 1. Okay, case 2. In this case, we're going to look at, in this case, 3x minus 1. So that one will be positive, the first factor. And in that case, that makes the second factor negative, right? We need one positive factor, one negative factor, because the two multiplied together must give you a negative, right? If that were greater than 0, then they'd both be positive or both negative. So 3x has to be greater than 1, which means x is greater than 1/3, and x minus 2, so x is less than 2. Okay, let's examine that case on a pair of number lines. And I'm going to put a 0 in. There's 1/3. And here's 2. And here's 1/3. And here's 2. So x is greater than 1/3. Strictly greater, circle it and go. And x is less than 2. And we do have some overlap here. So in this interval, they are both true. And that interval will give us the interval 1/3 is less than x is less than 2. And if we want to be formal about it, it would be the set of all x such that 1/3 less than x less than 2. And we can add that x is an element of the reals. So this is case analysis. Okay, and you'll be looking at being able to use all of the different methods to solve inequalities. And the questions in the book, which we're taking a couple of days to do, will ask you to try different methods. So just be familiar with the different methods, which again are back, up. Graphing the corresponding function, using roots and test points, using sign analysis, and using case analysis.